Hi everyone and welcome to the internet. What we're going to be doing in today's physics lesson is having a look at a process called electromagnetic induction. So hopefully by the end of this lesson you'll be able to actually describe what electromagnetic induction is and when it occurs. So to start us off, we've got 3 questions based around our previous lesson on the screen. Have a go at answering those in your books for me. I'm going to give you about 3 minutes to have a go at that. Okay, let's check those answers then. Obviously mark these if you've got them right. So our first question, how can we increase our actual motor output? So the first thing we could do is increase the magnitude of the current. Second one, increase the strength of the magnetic field. Third, increase the number of coils on the wire. Or we could have increased the length of the coil. So give yourself a mark for each of those you got right. The key thing here though is making sure you have said the word increase, because we're looking at increasing the speed of our motor, therefore we've got to increase each of those. If you didn't have the word increase, if you just said the magnitude of the current, it's not enough, folks. You've got to go careful with that question. The second one, the actual device that we have connected onto our motor is a split ring commutator. 1 mark if you got that one. And then finally, explaining what's going to happen in our little diagram in the bottom there. Then the left side is going to move up, because if we use Fleming's left-hand rule, we can see that you've got north to south, so you're pointing from left to right with your first finger, and your second finger should be pointing out of the screen in that case. So your thumb then points up, so the left side of the coil moves upwards. And then if we do the same thing, what we need to do is then flip your hand upside down, so your finger is still pointing north to south, your first finger, but your second finger is then pointing into the screen. So that means your thumb is pointing down, which means the right hand side moves down, and that gets you a mark. So add it up, it's a total of 6 in that case, because 3 marks for question 1, 1 mark for question 2, and 2 marks for question 3. Give yourself a score out of 6. Okay, so what we're going to look at today then is this process of electromagnetic induction. So if we think about what happens with a magnetic field, hopefully we remember from the work we did right at the start of P4, then when we look at a magnetic field, it's made up of these field lines. So the stronger the magnet, the more field lines there are packed closer together. If we then have a piece of wire that we just move within a magnetic field, then assuming it's cutting those field lines, so it's moving across those field lines and cutting them, then what we're going to end up doing is inducing a potential difference across the wire itself. So I'm talking about a piece of wire that's not connected onto any kind of power supply at all. If we have just a piece of wire and we move it through the magnetic field so it cuts the field lines, we are going to induce a potential difference across that wire. Now, there's another way that we can do this. We can also induce a potential difference across a wire if we actually make a magnetic field change around the conductor. So the key thing here is that the wire is cutting the field lines. How we achieve that, there's a couple of ways we could do it. But if the wire does not cut field lines, we will not induce a potential difference. It's only through cutting those field lines that this happens. So write down those 3 sentences for me in your books if you haven't already. I'll give you another minute to get that done. So what we find is that any time we have our wire cutting those field lines, then we're going to induce that potential difference. But we can increase the amount of potential difference we are inducing in one of 3 ways. So if we're asked how we can increase the potential difference that we're inducing, you pick one of these. First one is we can make the wire move faster, because obviously moving it faster means it's going to cut more field lines per second. We can use a stronger magnetic field, because that way moving our wire is going to mean it cuts more field lines because there's obviously more of them within that same area. Or we could use more wire. So generally that means we wrapped it into a coil and there's more of those coils in that place. And again, it just means that there's more of those field lines being cut by the wire in that same motion. So 3 ways to increase our induced potential difference: move the wire faster, use a stronger magnetic field, or use more wire. So get those written down. I'll give you another 30 seconds if you haven't already got them. Next one, question for you to have a go at answering in your books. Explain how moving the wire faster or using a stronger magnet produces a greater induced potential difference. So I'll give you a minute to have a go at answering that in your books for me. So what we need as our answer for this one is just the statement that it cuts more field lines per second. So if we move our wire faster, then obviously it's going to cut more field lines in that time frame. And if we use a stronger magnet, there's more field lines there, so the same motion means more field lines are cut. So it comes down to the same thing, we cut more field lines per second. Give yourself a tick if you got that right. So at this point we understand that if we move a wire within a magnetic field, we induce a potential difference across that wire. And that's all down to the fact that we've cut those magnetic field lines. If we now connect that wire into a circuit, then we are going to have a current flowing. Because if we've got potential difference across the wire, then current will flow. If we've actually got a current flowing through a conductor, then we generate a magnetic field. Think back to what we did right at the very start of this unit. We said that around a wire, then when current flows through it, we have a magnetic field around it. So as soon as we've connected that wire into a circuit, current is flowing and it's then creating its own magnetic field. So what we find is we've got a magnetic field being produced by our current carrying wire, we've got the magnetic field from our magnet, and then we're going to see a force acting on it because the wire is in an existing magnetic field. So what we're doing here is we're tying together a few of those ideas we looked at earlier on in the topic. So remember what we said, a current flowing through a piece of wire, that wire will then generate its own magnetic field. If that current carrying wire is in a magnetic field, then we will have a force acting on it. So make sure you've got those 3 sentences written down. I'll just give you another minute to get those jotted in your books if you haven't already got them. If we then consider the direction that this magnetic field that we're producing is acting in, then it's going to be in the opposite direction to the field that produces the potential difference in the wire. So we've got 2 magnetic fields, the one that's going to produce the potential difference in the wire and the one that is produced as a result of the current flowing through the wire. And those act in opposite directions, and we know that because of the law of conservation of energy, because we can't have them going the same direction, otherwise basically we've created energy, which isn't possible. So due to conservation of energy, the magnetic field produced is in the opposite direction to the field that produces the potential difference in the wire. Again, I'll leave this up for about another 30 seconds so you can jot those points down. So what we're actually going to be able to do then is there's a little experiment that we can do. And normally I do this in the classroom because it's quite a fun one. And if you have a piece of metal pipe lying around at home and a small magnet that will fit down it, you can do this yourself. What we're actually going to do is we're going to drop a magnet down a metal tube. And what you're going to have a go at doing is predicting how long it's going to take that magnet to fall through the tube. Now, ordinarily we'd obviously do the timing of this, we'd record it with a mass that's exactly the same and all of these other things that we could do, but we don't have half that equipment, unfortunately. So what I do have is a little video to show you this, so you can have a little look at the video. But before we do this, I want you to predict how long it's going to take a magnet to fall through a tube. Do we think it's going to fall at the same speed as a stone of the same mass? Do we think it's going to go quicker? Do we think it's going to go slower? And if you can, try to suggest why that may be. So to start off with, we've got a piece of copper pipe just attached onto our clamp stand, just held nice and vertically. Here's my virtual assistant for the day, and what he's got there is just an iron ball, so not magnetic. And as we drop it through the tube, then we record the time as 0.02 seconds. So a non-magnetic iron ball, 0.02 seconds. This is the same size spherical magnet, and as we drop it, it takes much longer. That one takes 4 seconds to actually fall through. So what we would see here is that key difference, where the magnet is taking much longer than the ball. And what you can see on the screen now is just your explanation for this. So as we actually drop that magnet through the copper tube, then what it does is it induces that potential difference in the copper. That potential difference obviously generates the current causes its own magnetic field and makes the magnet fall slower. Okay, let's make sure we've got an explanation written down in our books for what we just saw in that demonstration. So what we see is when we just drop the metal ball through the tube, so the non-magnetic metal ball, then we won't see any difference. It will literally just fall, because where it doesn't have its own magnetic field, then it just drops through the tube. When we trade that for the magnetic sphere, then what we see is that as the magnet's falling, obviously we're getting a changing magnetic field. And as a result of that, we will induce a potential difference in the pipe, because the pipe is made of a conducting material. As a result of the potential difference that we've generated in the pipe, a current will then flow, because where it is a pipe is a complete circuit at the end of the day. And this current flowing through the pipe then produces its own magnetic field. So at this point we've then got two magnetic fields, one from the magnet itself and one from the current flowing through the pipe, and those fields are in opposite directions to each other. As a result of that, what we see is the magnet is repelled. So because we've got this repulsion between the actual pipe and the magnet, then it makes it fall slower through the tube than when it was just a metal ball without this effect. And this is actually how we can use a metal detector. So if you've seen those people wandering around in fields or on the beach with those metal detectors sweeping them across the ground, the way it's actually working is, as it comes across a piece of metal in the ground, then we end up generating this magnetic field, which then generates, obviously, this beep on our machine. So what we're seeing is our electromagnetic induction to allow us to detect metals in the ground. So make sure you've got those points written down. I'll leave it up there for another minute or so just to give you a chance to really think about it and get those written down. Last thing to do today then is the plenary. So those of you with target grades up to a grade 5, it's the questions on the left. Those of you with target grade over a grade 5, it's the questions on the right. So I'll leave these up here for about, I'll give you 5 minutes today to have a go at these. So make sure you're writing your answers in your books. So don't just sit there and do nothing. Please do answer these questions in your books. As always, you can find the answers to the plenary over on my website, scienceright.weebly.com. You'll also be able to find that under the Internet tab. Just select the week that we're in, and then you'll be able to find things like the lesson PowerPoints, the answers to the plenary, any additional work, and if there's any little experiments I thought you could do at home, then they're there too. So have a look and get using that.